So thank you very much, Haoyi, for being here in Madrid. We are honored to have you here and enjoy the talk. Thank you.
Thank you. Yeah, hello. Should we plug something in? Oh, here. Yeah, I think this should work. Do we need to turn that on? Oh, okay. I think we're good. Okay, cool. Okay, hello. So my name is Haoyi, and this presentation is better Scala builds using the mill build tool. So the motivation for this talk is that kind of the build tool complexity has been one of the long-standing problems in the Scala ecosystem. So lots of people want to use Scala, they use SVT, get confused, it's hard to configure, it doesn't quite do what they want, and it spends lots of effort when they really want to be working on the application code. So this talk will kind of explore what are some of the problems with SVT, why are build tools difficult, and given that, like, is there a better way to do it? We'll explore one of my open source projects, which is a mill build tool, and see how it does things differently from SVT and the other Scala build tools out there in the ecosystem. So about myself, I've been working with Scala since 2012. So lots of projects on GitHub that many of you probably used. I work on developer tools professionally, so CI systems, testing systems, deployment systems, and so on. And I'm author of the book Hands-on Scala Programming. So this talk will have 4 sections. First, we look at like, is it as good as we're going to get, or are there actually opportunities for improvement? We look at what is mill. This mill is an open source project of mine that is an alternate build tool to SVT. We look at why is mill interesting and what are some of the key ideas behind mill. So first, like, can Scala builds be easier? So the biggest problem with SVT is that it's not that it doesn't do what you want. It's that SVT is easy to configure. And that is, I can stand here. Oh, sure. Okay. So SVT is powerful. It can do everything. It's flexible. It can be fast if used correctly. But if used correctly is often the challenge. So it's not easy to use it correctly. And if you don't use it correctly, suddenly your performance is not so good. Suddenly ID support doesn't work well. Suddenly the extending it becomes difficult. And you have alternatives like Scala CLI, but that only really works for smaller projects, doesn't work for larger ones. So, like, for example, even just running SVT requires a documentation page because you need to open a shell. If you don't use a shell, it'll work, but it'll be slow. If you do use a shell, you must remember to use reload. You must remember to re-enter the shell if you Control-C to interrupt something. And like, there's a lot of trickiness, and it's not challenging, but it's work you don't want to do when you want to be busy working on other things, like in your actual project. Parallelizing tests was one issue I hit recently, where it took me 2 hours to figure out how to parallelize tests, and in the end I had to ask for help on Discord because there's a whole lot of test parallelization flags that you can turn on or off in different scopes in SVT, and they all do different things and interact in unusual ways. Like, for example, you turn on parallel execution. You also might need to turn concurrency restriction, but if you use test fork is true, then you need test fork parallel, and then you need a separate concurrency restriction to be added. And like, it all makes sense to some degree, but it's very challenging. And I personally had lots of trouble getting this to work correctly. And lastly, the last problem is IDE support. So if you look at SVT in IDE, so over here I have the SVT build for the Gatling code base. So Gatling is a popular Scala open source load testing framework. And you see, IntelliJ does have IDE support for SVT. You can jump to some things, but when you jump to other things, you find you just get stubs. So in this case, I haven't set up the sources, so you don't see the source code here. But even if you do have the sources, all you see is the documentation saying that this is the dependencies of the library dependencies of the module. And what you don't see here is what you actually care about, which is how was this computed? Where is it used later? Basically, all the things you'd expect to find in an application code base, you can't really find using SVT using your IDE. So in contrast, right, if you open up any random project in this, any random file in this code base, so let's pick one at random. You pick any random file, even without documentation, you'd expect to be able to jump to any name in this file. So even if you don't know what it is, the GitHub is there, but you haven't seen it. Google doesn't find what you want. documentation Scala doc is missing, you can still kind of find your way around the code base, internal files, external files, and library files. And you never really get blocked. Whereas with a build tool like SBT, when you try to jump to something, like sometimes it works, and sometimes it just doesn't, and you're just stuck, and there's no way for you to proceed figuring out what's going on here. So when you think about it, like the fundamental problem in this case with build tools like SBT, but also Gradle and Maven and others, is that they're built around like global mutable variables. So something like library dependencies is really just a global mutable variable, and just because we wrap it in a doesn't make it anything different. So global mutable variables, they're set somewhere else, they are read somewhere else, and you don't know where those somewhere else's are. And it's exactly the same with SBT, where someone is setting this library dependencies, someone is reading it, but neither humans nor IDEs can figure out where it's used or where it comes from. And in contrast to like application code, where you generally avoid global mutable variables exactly for that reason. And the last challenge is extensibility. So the first thing about SBT is that it has a lot of plugins. That's good, but it often requires a lot of plugins to get anything done, which is bad. So most people have this laundry list of plugins that they copy paste from project to project. All the versions are kind of arbitrary when they first copy paste it off Google or Stack Overflow. And like maintaining this list or trying to put together a list first time can always be a big challenge. Like someone who wants to start a new project and auto-format their Scala shouldn't have to go and find like the correct open source plugin in the Scala ecosystem to do so. And sometimes you need to do something that's not in a plugin. Like sometimes you need to do something special. Sometimes you have a special bill of materials you need to deploy, or a deployment artifact you need to send your infrastructure team, or special linter you're trying to roll out. In this case, we're just using a strawman example, which is like count the lines of code and save it in a runtime resource file. And with SBT, it's not difficult, but it's not as trivial as you'd expect. Like I would expect this to be 30 seconds by any new graduate engineer programmer would be able to write this out. With SBT, although the core business logic or build logic is actually very simple, it's surrounded by a bunch of other stuff that can be very easy to get wrong, like things like remembering to use def.task value, things like making sure things are in the right scope of compile or unscoped. And all of these are things that, while not challenging, it's a lot more challenging than it should be for such a simple task. And for more complicated plugins or extensions or custom build pipelines, it gets much more difficult. So that's kind of the three big problems at SBT, where it can do everything you want, but it's really not easy enough as people would like. And people ask, like, is it something wrong with SBT? And the thing is that build tools are fundamentally pretty complicated pieces of software. So you need to handle a lot of different things in your build. So apart from your application code, which you care about, apart from whatever customizations you want to do in your build, like maybe you want the line count as a resource file, that's your build logic you want. Your build tool needs to handle all these other things, like who depends on what can be parallelized, how things run from CLI, how are things cached, how custom tasks are defined, how tasks pass data to each other. So all of these things, like if you try to define an API to model this naively, it would easily be a very complicated API, and that's why build tools are typically very complicated and hard to use piece of software. So earlier I talked about SBT, but Gradle, Maven with its plugin system and others are also not very easy to use. So that's the kind of bottom line. Like, can Scala builds be easier? Maybe. Like build tools are hard, but there are lots of areas where SBT it's just a lot more complicated than you would hope. So the next section of this talk, we're going to look at the Mill build tool. So Mill's an open source JVM build tool. It's been around quite a few years now. Originally just targeted Scala, now also targets Java and Kotlin. And it mostly does the same thing as SBT, Maven or Gradle, but tries to be better at the problems I mentioned earlier. It's quite widely used in Scala ecosystem. It's not dominant, but things like Scala CLI, Corsair, all the commonly Haoyi libraries use it. So it's quite battle tested in Scala. And the documentation is on the website if you want to see more. So a Mill Hello World project looks something like this, where I define an object foo module extend Scala module. This creates a module in the foo subfolder of your project. I define a Scala version, IB dependencies, a nested test suite, foo.test, nested within foo, with its own dependencies and test framework configured. And I can compile, run, test, assembly, and so on this module. So far, nothing very special. This is a slightly more involved example showing a HTTP4S to-do MVC application. So it has the Ember server, Scalatags, Circe, and integration testing included. So this one I can show live. So if I go to It's HTTP4S. I think it's this one. Let me make this a bit bigger. So this is the project we saw on the slide earlier, the build config. The application code is a simple web app with a HTTP4S Ember web server, routes, and Scalatags templates. If I run, I can run unit tests with this, I think. I can do mil test. This will build the build file, build the project, run the test. I can use run background. Let's run this mil -- watch run background. This should load it up on a new, in the browser. If I go localhost 8084, this is my HTTP4S web server. I can make updates to it, like instead of to-dos, maybe I want to do hello. And now once it spawns up, it'll be alive. To-do is hello. So this is just a short demo of like mil in action used for a small project using real dependencies. So people often ask, like, what does mil support? And the answer is mil supports most of the open source projects you find out there. So things like executable assemblies, Scala native image, all the different format, autofix, linters, different test frameworks, and so on. It won't support all the custom things you have internally. So if you have your own custom SBT or Gradle plugins, mil obviously won't be able to have equivalents because we don't know about those. But at least the things that are open source on GitHub, like broad ecosystem, mil generally has support for most of that. So that's a quick tour of mil. So far we saw mostly mil doing what any other build tool can do. So let's look at what mil can do that other build tools like SBT don't do as well. So I think the reason why mil is interesting is that it's just easier to get good performance out of mil. It's easier to get good ID support and navigate your build. And with custom logic or custom build pipelines and so on. So in terms of performance, we use a Gatling code base we saw earlier as a proof of concept. So Gatling is normally built using SBT, just as an example build, we port it to mil manually. And it's complete enough that all the tests pass in both. So it's not just a hello world port, but actually all the flags right, dependencies right, Scala version, Java version, and so on. So Gatling's not a small project, like 20 sub-projects, 80K lines of Scala, which is quite a lot of Scala code. And everything works in mil as well as SBT, at least in our proof of concept. So we did benchmarks using mil and SBT. And the first thing we realized SBT, which you probably already know, is it has two performance profiles. One is if you use SBT, like use any other command line tool, you have to run SBT something from the command line. It runs cold every time it starts up a new JVM. And it's easy, but it's very slow. If you use SBT hot, like it's documented in the instructions, open up SBT REPL and run your commands in there, remembering to reload and to rerun the REPL if it gets interrupted. It's much faster. And the thing about mil is that it's not significantly faster than SBT hot. It's about as fast as that. But it just automates the management of the long-lived background server. So instead of you having to babysit this REPL process yourself, remembering to reload and restart it, mil does that automatically in the background for you. So you can just run mil like any other command line tool, and it largely will just transparently does the right thing. So mil has a bunch of other things that are quite nice, like we already saw watch and rerun. Mil's test parallelism is a lot easier to configure than SBT. It's one flag, and generally it's self-tuning enough. You don't need to fiddle with the other things like concurrency restrictions or parallelism number. Mil has selective test execution. So if you make a pull request, you can ask mil to compare before and after the pull request, like on main and on your feature branch, and ask like what modules tests are downstream of that pull request change. You can ask it to render like a tree of how the pull request touched this task. So this task is downstream, this task downstream, and therefore test has to be retested. And you can ask mil to run only the downstream test, which is very handy in a big monorepo, where you may have many other unrelated tests that you're just wasting time running because they're not related to the code being changed in your pull request. Mil can do incremental assembly jars. So in a big Spark submit assembly jar that may be 200 megabytes, may take 20 seconds or more to assemble because it's a large thing. You need to zip up all the dependencies. But with mill, doing it incrementally, like you add a new file and you recompile and update the assembly, can be done in 1 second, just because assembly jars actually are just zip files, and zip files can be updated very efficiently using Java and IO file systems. So for some reason, the existing build to the SBT and Gradle and Maven don't do this, but mill does. And as a result, iterating on assembly jars in mill is much faster than Maven, Gradle, or SBT. The last thing that's worth looking at is a Chrome profile. So every command you run in mill generates a Chrome profile, and I can show this to you. So if I do mill clean and mill compile in my Gatling mill example code base, you'll see that it generates this mill Chrome profile.json file. So this is not readable, but it's a standard format that Google supports in the Chrome browser. Every Chrome browser on everyone's laptop has this Chrome tracing UI that lets you visualize profiles kind of just built in. You might not use it, but it's there. So anyone can just drag and drop this file into your Chrome browser and see exactly where the time is going in your SBT code base, in your mill build, sorry. So you can see where the build is using all the calls. You can see where the build is bottlenecked. You can see where the build is very bottlenecked on one thing. Even when your build hasn't finished, you can do this. When your build has finished, you can update it and see more. And now you can see that after Gatling call compile finish, a bunch of other tasks kicked off. So this is very convenient, and it's just built in. You don't need to install plugins or install Gradle Enterprise, build scan servers or anything. And when you often have the question like, why is my build taking so long? This gives you an immediate answer. Like Gatling call compile is clearly the bottleneck. If you want to do something about it, even if you don't know anything about Gatling and don't know anything about mill, you can already see there's some ideas of maybe I can refactor this code to break up this module. Maybe I can break up some of these other modules, and that would improve your day-to-day work, like iterating on your code base. So that's the performance angle of mill. Like it's not more performant than SBT. SBT can actually do all these things. It does it for you, and it makes it a lot easier for it to do it. So you don't need to worry about getting it wrong and having a poor performance out of the box. The next thing we're going to look at is the ID support. So if you compare the ID support for Gatling with SBT and Gatling with mill, which I have on the left, it's on the right. So SBT is on the left, mill's on the right. If you look at the Gatling core module, let me just jump to that. You'll see that they actually have a lot of very similar information. Like they both need this netutils dependency. They both need this quick lens dependency. They both have commons and JSON path dependencies and the corresponding test dependencies. So they actually have all the same information because it's really modeling the same build, and the Gatling project needs this configuration in order to build and test. But what's different is that where when SBT, when you jump to a task or setting key, it kind of gives you this stub, which is really just a global variable. You have no idea where the value is coming from or going. With mill, rather than using global variables, mill uses overrides to configure your build. So these are familiar to anyone who uses object-oriented programming. For example, fork args, I don't know where that came from. I can click on IntelliJ's override gutter icon and just jump to it. I can see fork args comes from run module. I can see fork args is used in runner, which is used in run background and run forked, which is used in run main and run. So this way, rather than just being an opaque setting that you set and hope it does the right thing, mill really lets you explore how your settings interact with the build pipeline and end up affecting the thing you care about. So I set fork args, but really what I really want to know is how does it affect when I run my code? And mill lets you see that. I showed you how you can trace it downstream. You can also trace it upstream. So let's say you don't know how this final main class is computed. You can jump to it. There's no Scala doc here, but that's fine because you both have the implementation as well as the upstream tasks. So I can jump to this. Again, no Scala doc. Again, you can see from the implementation what's going on. You can see this either computed from the main class, at least this one has a bit of Scala doc. If you explicitly set the main classes there, or local main classes, which is how it's using, which uses this class graph project to discover the main classes by scanning the class path. So none of this ID support on the right you see with mill is kind of special, but rather this is just ID support that you all use day to day in your application code. In application code, you are used to not having documentation. You're used to having like something that ChatGPT can't answer because it's proprietary. But nevertheless, you can navigate around your application code by jumping the definition, finding usages, finding overrides, going up and down the class hierarchy. And what mill does is that because mill uses objects, classes, and methods and overrides to define your build, your IDEs like IntelliJ and VS Code are able to navigate your build very easily, even though they don't have any special support for mill. They just treat it like any other Scala code and are able to navigate it much better than they can navigate any SPT build, because SPT has its own concepts that IntelliJ or VS Code are not aware of. So that's the IDE support demo. The last demo is the extensibility, where mill has both a lot of built-in functionality and it's also able to let you write code to just do stuff in your build in a way that's much easier than SPT or other build tools. So first, in terms of plugins, mill generally needs much fewer plugins than SPT to do common things. It still has plugins. For example, this Scala fix functionality is in the plugin by a third party, Joan Goyer. But things like Kotlin, things like Jupyter, JUnit 5, things like JMH are all built in because everyone needs those. We need those. So rather than having this big plugin ecosystem that different people contribute different components, we just built all the common ones into mill, and it's very easy to integrate things in mill. So we just did it. So sometimes you do need customization though, and the difference with mill is that if you want to customize your build, you often don't need a plugin to do it. You can just do the thing in your build directly, and I'll show you what that means. So if I open up, let's find the right project. If I open up custom Scala here, so over here on the right, I have like the most basic Scala project. You see there's almost no config in it in mill, and that's because mill has defaults like Maven or SPT. So if you don't want to customize sources or dependencies, there's really nothing to say. You just say, I have a Scala module in foo, in a foo subfolder, which is here, and it has a Scala version, and I can just go to my terminal, mill, like foo.compile, for example, to compile it. So let's say I wanted to do what we mentioned earlier, which is like count the lines of code in this project and save it to a file. How do we do this in mill? We already saw how to do this using SPT. With mill, custom tasks are just methods. So in Scala, methods are def, for example, line count equals task block. And you call other methods in them. For example, you can call foo.all source files. And if you're not sure which method you want, again, there's Scala documentation. You can jump to definition and see the implementation and so on. So in this case, we want all source files. I'm going to map it to the file paths. I'm going to os.read.lines. This is the standard like oslib file system library. I'm going to sum them up. And that's all you need to do to define a custom task using mill. So it's just using very standard Scala syntax, very standard Scala methods and method calls, except you just wrap each one in a task block. So now that I have this done, I can do mill show foo.line count. Okay, line count is 17. The first time you compile it, it's a bit slow. After that, it's much faster. I can do mill inspect foo.line count. You can see that we capture the Scala doc for you automatically, so you don't need to go put in a separate string. We get a file name and IM number for you. We capture the input, so foo.all source files is captured automatically. And that's all you need to do to define a custom task in mill. So although it's Scala just like SPT, it's a lot more normal Scala than SPT, special like settings key, task value, def.task syntax. So we have a special line count task. We haven't integrated it into our resources yet. So to do this, mill uses overrides. So in general, to customize existing tasks, mill uses overrides. So you can say override def resources. Again, you're not sure which one you want. You can ask IntelliJ, it'll help you. And I can say I'm going to write to this task.destination folder, linecount.txt, which I'll explain in a moment, the line count as a string. And then I'm going to append to my resource path, path reference to my destination folder. So what's this destination folder? So every task in mill gets a folder on disk that's dedicated to that task. So this is very convenient because you don't need to worry about collisions between files on disk, someone writing to the wrong file, two plugins using the same name and colliding. So in most build tools, the file system is like the biggest global mutable variable. Anyone can read to anywhere, anyone can write to anywhere, and therefore you don't know who's reading or writing to anywhere, and it becomes a big mess. In mill, if I show you this now, if I show you the resource path, you'll see that because I kept the super, so the original resource folder is there, But this new task.destination folder, or reference to it, is this out full resources.dest. So only foo.resources gets full resources.desc. Other tasks will get like line count.desc or compile.desc, and they'll never collide. So inside full resources.desc, you can see that there is my line count txt file. And now I can say /mil foo.run. And you're able to use this line count file at runtime. So I've integrated it into the resources, and the example application code, which is just a small Java project that loads it from line count.txt, is able to access the code. So let's go one step further. So instead of having a line count txt, how about if we want to have a line count HTML file? Again, this is a bit arbitrary, but in many cases, you do want third-party dependencies in your build, right? Maybe you have a special code generator you want to run, maybe a special linter you want to download from Maven Central. All of these things are common, and just as a representative example, let's say we want to render line count as HTML instead of a string. So Mill doesn't come built in with like HTML templating engines. You can't say import Scalatags or text are all in your Mill build just like that. But Mill does come with the ability to import libraries from Maven Central. So I can say import commonly Haoyi, Scalatags, like 0.12.0. And just like that, if I reload my IDE, just to show you, this should start working. And now IntelliJ is able to see that Scalatags is available. I can jump to Scalatags in my IDE. You can see it in the external libraries list. And I can immediately start using it. For example, I want def HTML snippet as a task. And I say I want a div with h1 line count and a paragraph, which is the line count as a string. And I want to render it. So now I can say mill show foo.html snippet with my new HTML rendering custom task. I can see the value computed at build time using the third-party library. I can look at it on disk, HTML snippet.json, see that we store the cache values in the JSON file together with some other metadata to let us decide when to invalidate things. And lastly, if I replace my line count in my resources, such as HTML snippet, when I do mill foo.run, I'm now able to take my HTML using a third-party library, pre-render it at build time, and take the resource and use it at runtime later. So I think what's most interesting here about the mill build customization is that there is no mill HTML rendering Scalatags plugin. There is no mill line count plugin or mill file system counting plugin. Really, you just write normal code here using normal Scala methods, using normal Scala overrides and supers. And you all learned methods, overrides, and supers like 20 years ago in school, so you know how those work, and they work the same here. And that's all the concepts you need in order to customize your build. And you even use normal third-party libraries. So you don't need to find a Scalatags plugin, you just use Scalatags. If you want to use some particular binary, you just use that binary or library without having to first find the plugin that wraps that library that often is more poorly maintained and less well documented than the original project on Maven Central or GitHub. So that's the extensibility angle, and this is a demo I showed earlier. So I think that's why mill is interesting, right? The performance is a lot easier to get good performance. SBT can be as performant if used correctly, but mill is easier. The ID support makes it easier to navigate your build. You just can jump up and down your your method call graph and your build graph, just like any other application code base. And it's easy to extend in that you can just write code to do the thing you want using the normal libraries that you already know how to use. You don't need to find a special mill plugin or find a special like mill plugin API in order to implement this logic. You can just write the logic and it does what you want. So let's look at some of the key ideas behind mill that lets you do this. Everyone wants easy performance, understandability, and extensibility, but how come other build tools aren't able to get it? So mill has three main core concepts. The first is that the build graph is a pure functional program. The second is that your build is this object-oriented hierarchy of modules. And the last is we use this direct style DSL rather than a staged DSL. So the first bullet for pure functional build graphs, the interesting thing is that most build steps are of the form do thing to inputs to make outputs. And in mill, it's spelled like this using Scala syntax, but it's really the same thing. And if you look at all the things that the build tool does, whether resolving dependencies to make jars, running CodeGen and IDL to make source files, compiling source dependencies to make class files, they're all of the form do something to inputs to make outputs. So Mill uses that to define your build. So line count is a pure function that takes your all source files and runs a pure computation to read them and return the lines. And you could do this imperatively on the right, like as a side effecting callback, which many build tools do. Most build tools, in fact, like you hook a callback, it will just randomly read from some random file on disk and write to some other file on disk. That's kind of standard for things like make, rake, Gradle, most of JavaScript build tools. What's the difference between the two is that although they both have the same logic, really, on the one on the left, we don't just read and write to random places on disk. We only read to the things that are given to us as parameters, and we only return the value at the end that we computed. So that means that we are not doing any side effects of mutating global state ourselves, and even things like files in the .destination folder are not global state anymore because you're not meant to read. You're not meant to write to other people's destination folders. You only write to your own. And once you have this kind of pure functional task that only reads its inputs and writes and returns its output, it can be parallelized, cached, and scheduled very easily. Like on the right, we don't know who's reading and writing to what file, so you can't really safely parallelize them because someone's going to conflict and stomp over each other's files. But on the left, we know where they're going to read from, where they're going to write to, and so Mill can safely decide what to parallelize without you needing to do anything. So you just write the business logic here, or the build logic, so to speak, and Mill takes care of all the rest. So the other thing is that pure functional programming is what makes jump to definition useful. Many build tools traditionally have this global variable data model where there's this variable, in this case it's called test/unmanaged source directories, and someone else is setting it and you don't know who, because anyone in your huge code base could be setting it and you can't find it. And multiple people are setting it, you don't know which one is the one you care about. Whereas in Mill, rather than global variables, Mill uses methods, pure functional methods, in fact. So when I say all source files, I can jump to it, see its implementation. If I don't know what all sources is, I can jump to that, jump. And generally, because Mill has pure functional build steps, it makes the IDE much more useful at navigating them in a way that the same IDE just cannot navigate traditional build tools which are built upon global mutable variables and configuration. So that's the idea of pure functional build graphs, where I think it's quite unique to Mill. Most other build tools have some of the ideas, but don't have it integrated so nicely into the IDE and language. The next thing we're going to look at is object-oriented build definition. So every build tool needs you to provide some way to define these templated customizable graph computations. And this is a bit of a mouthful, but you consider a 3-module Java application below, like with foo.bar, foo and clocks modules. They all have sources, they all have compile, they all have class path that feed into each other in similar ways, but not quite the same, right? Like foo.bar.class path has no upstream, but foo.class path does have an upstream bar.class path that it uses. So they are similar, but they're not quite the same. You need to customize them specially. And there needs to be a graph because you need some way to decide who runs first, who runs later. And you need to have computations on each step because sometimes you need to discover the main class. Sometimes you need to compile something or make an assembly. So it's actually every build tool needs a way to define templated customizable graph computations. And templated customizable graph computations are quite a sophisticated concept. Like any of us try and define an API to make a templated customizable graph computation, it'll probably be quite a complicated API. And even if you don't need to do it yourself because you use a plugin, the plugin authors need to do it. So the plugin authors have problems with the API. They'll get it wrong. Your plugins be flaky, slow, or buggy because they are just humans too trying to struggle with a completed API to make their build plugin work. So Mill also needs to do these things, but Mill uses a lot of things that you already know to do this, which is object-oriented programming. So everyone knows object-oriented programming. It might be complicated, but you already learned it 20 years ago in school. And the idea is that, well, the graph is your method call graph. The templates are your classes. You can instantiate your class multiple times, so multiple copies of the call graph. And you can customize your classes by overriding it. Either you override it in a single method in an anonymous class instance, or you override it for a subclass, and many instances can use. And the method bodies are the computations. So these templated customizable graph computations actually map very cleanly to the idea of object-oriented programming with methods, classes, objects, and overrides, and even supers. So earlier when we say object foo extends Java module, this is actually literally a JVM object whose name is foo and extends a Java module class or trait. And like any other class or trait you extend, you get a bunch of methods. These methods call each other, like foo sources gets called by foo compile, called by foo class path, and so on. And like any other JVM like method call graph, if you add like a new line count method that calls all source files and override resources, call super resources, and call line count, I don't need to teach you how this affects a call graph because you already know how methods, method calls, supers, and overrides work. And it's not trivial, but you already know. And once we have this graph, we can do interesting things. Like we can say that compile and line count, this blue and red sections of the graph can run in parallel because they don't depend on each other. But assembly needs to wait for both of them to complete before it runs because it depends on both. Foo.line count, foo.compile, foo.assembly, they all have names. So we can use the name to tell you how to call them from the command line. So foo.line count in the Scala code is literally foo.line count from the command line. That's how you name it. There's no special mapping of how to name the task. And similarly, you can automatically give every task a JSON cache metadata folder, metadata cache folder, as well as a .dest folder. That's this task.dest we saw earlier, in order to put its file outputs. So if every task puts its file outputs in .dest, then you never get collisions on disk, and this scary global mutable file system becomes a local immutable file system that's much easier to manage. And although it's technically still I/O, for all intents and purposes, can be treated as like pure functional values. And lastly, Mill is able to handle invalidation for you. So if you touch the resource folder, that's now called super resources because we overrode it. Mill can just do a breadth-first search, see that foo.resources downstream, foo.assembly is downstream, so Mill knows he needs to recreate the assembly. Mill knows where the assembly is stored because it's all stored in the .dest folder, so Mill knows where to delete it. Mill also knows that it can reuse compile and line counts because they did not get changed. And Mill knows that the compile and line count metadata and files data is all in these standard locations on disk. So all of this can be done automatically because we really constrain what the user is able to customize in your tasks. So because the user is constrained, the Mill like build tool is able to do a lot more for you because everything is very predictable. You don't have the users doing special snowflake tasks that the build tool doesn't understand. And so when you look at this code on the left, what's most interesting is there's no code related to parallelism or caching at all. Like the parallelism caching you get for free, but you don't see any like futures, threads, locks, or executors. You don't see any like cache key computations, cache reads, cache writes, cache invalidation logic. You get all that, but Mill does it, so you don't need to do it yourself. You basically write pure build logic here, like summing up the lines of code and writing a resource file, and Mill just handles all the build logic for you. So that's the idea of object-oriented build definitions, where like functional programming is cool, but the idea of object-oriented classes, overrides, and methods is really important in how Mill works. The last thing we're going to look at is the idea of a direct style DSL rather than a staged DSL. So comparing the Mill build config to the equivalent SPT build config, like they're both Scala, but they are very different kinds of Scala, right? Like the Scala you see on the left looks normal Scala, except for these task things. And the Scala you see on the right is that kind of weird, and you'll never see code like this in application code base with these slash colon equals plus equals def.task and so on. And kind of the bottom line for this is that the problem with SBT is that it's really a two-stage program where, and stage one, there's all these Scala concepts like override methods, Scala doc, inheritance, call graph, and so on. But what's important is that after stage one runs, you get this data structure, and stage two has all SBT concepts. Like SBT has doc strings rather than Scala doc, and IntelliJ knows Scala doc, IntelliJ does not know doc strings, so IntelliJ can't show you your SBT doc strings in your PCAT documentation shortcuts. IntelliJ knows about the XScale scope, but IntelliJ does not know about the four-dimensional SBT scope hypermatrix. So IntelliJ isn't able to see where these variables come from because IntelliJ doesn't understand SBT scoping, it only understands Scala scoping. So that's kind of the problem for both humans as well as IDEs. Your new grads don't know this stuff. IntelliJ VS Code don't know this stuff on the top right. And that's why, although it's Scala, you get some IDE support, it's much less useful than you would hope. So Mill does a lot of work to try and squeeze everything into the bottom right. And so in Mill, your Scala doc are your doc strings. Mill, we use overrides, are your Scala Java overrides. Mill, we use the XScale scope. Your objects tree is your module tree. Your method parameters are your CLI like parameters. Your traits are just Scala traits or classes. And they take some work to do this. Like for example, capturing the Scala doc as strings we can use at runtime require the compiler plugin to like just read it from the source file and stuff in the annotation so you can read it using Java Reflect later. But in exchange for that work, what happens is that everything kind of just gets squished into all the concepts that both humans and IDEs understand. So IntelliJ knows doc strings, knows Scala doc, so it's able to show you this stuff in your IDE. IntelliJ knows overrides, so IntelliJ is able to navigate to show you this is what was overridden. IntelliJ knows methods and call graphs. IntelliJ can navigate up and down the build graph because as far as IntelliJ is concerned, it looks just like any other method call graph. So that's a kind of important thing that makes a mill really easy for humans and IDs to understand. So if you go back to this list we saw at the start of the talk, which is like why build tools are complicated, mill actually has to handle all the same concerns as SBT, Maven, or Gradle. Like mill doesn't skip any of these. Mill has to model them. But what makes mill unique is that mill models them rather than using custom concepts that are unique to mill, mill models them using concepts you already know. So many of the concepts are just methods. So who depends on who runs in what order, who can be parallelized, how do I define custom tasks? All of these are just methods, and you all already know methods. You already know how call graphs work and method calls work and so on. So I don't need to teach you how this stuff works. Although in other concepts, in other build tools like SBT or Gradle, there's be a special task concept with a special parallelism concept and so on. Similarly, the things which are not just methods are usually just modeled using objects and classes. So the name of the task is just object.method, like fully qualified name. And similarly, where they read and write to disk is just object/method, like path. How do you manage repetition when multiple modules have similar things? Well, they're just classes or traits. How you customize modules are just overrides. So by using these like functional programming concepts like the call graph and object-oriented concepts like classes, objects, and overrides, Mill's able to answer all these questions and kind of model all these things in a way that people can understand, not because it's simple, but because you already learn how to do it. Like object-oriented programming, pure functional programming are not easy concepts, but because people already learn how to do it as part of the day-to-day work, Mill is able to leverage that. So you already know how Mill works, even if you've never touched Mill before. So those are the key ideas behind Mill. The pure functional build graphs, the object-oriented build definitions, and this direct style Scala DSL rather than SBT's like two-stage DSL. And I guess this is the last slide. So to wrap up, like, can Scala builds be easier? Like, I think they can. And I think Mill is interesting because, for one, it has a lot of kind of concrete advantages over SBT. Like, it's easier to use to get good performance. The ID support's easier to navigate. It's easier to extend. You just write normal code and use normal libraries. You don't need special plugins and auto plugins and things like that. But apart from the concrete improvements, I think the ideas are also very interesting. This idea of pure functional build graphs and object-oriented build definitions with classes, objects, overrides, and supers. And the idea of a direct style build rather than SBT stage DSL is really what makes Mill very special. So the documentation is at the bottom, and here's my email, and thank you for listening. Cool. Yeah. Yeah, I guess we're done.
Thank you very much.
So you said the user don't have to manage anything related to parallelism, right? So out of curiosity, what do you use for parallelism inside Mill? Like plain features or Katz effect or something else?
We use Java util concurrent thread pool executor. So very, very naive. It's all hidden deep inside, so you generally don't care. Now we have now we have a priority queue, so we are able to prioritize certain tasks over others, and that's basically it. So I guess the thing about the Mill task is that the concurrency is usually very low. So things like futures and Katz effect, I think we do use futures, but we don't use a lot of the fancier parts. Mm-hmm. Things like future and Katz effect are most important when you have very high concurrency. Like when you have too many concurrency and not enough threads, then it becomes a problem, right? Or you can't spawn 10,000 threads to cause a machine to lock up. But most build tasks are very expensive. Like compilation is expensive, like generating containers or assemblies is expensive. So your concurrency is usually like 10 or 15 or something. So you just spawn 15 threads and let them run, and it's usually enough. Yeah.
Thanks.
Yes.
Yeah, thank you for the talk first.
Sure.
It was a really good one. I touched a little bit of Mill, but a few years ago. And for example, for support for Scala native or Scala JS?
It supports both.
Yes,
Yeah.
supports both. Okay. So it's you only have to change a few things, no? I understand in...
The model's a bit different from SBT. So SBT, you can copy paste the project, and Mill, you actually have multiple copies of the project, one for .js, one for .native, one for .jvm, for example. There's documentation on the website how it works. It's not quite the same as SBT, but you can do all the same things. So like all the commonly Haoyi libraries like uPickle support all three platforms, and it works reasonably well. Yeah.
Okay. Yeah. If anybody has a question, also and Mill, you run it on JVM, no? You cannot run it on Graal or.
It's a hybrid. So if you look at the
let me put the screen also.
Sure.
For the screen.
Yeah. So if you look at the performance of this, right? Like if I time./mill __ compile. You'll see it finishes in like 100 milliseconds. So this is much faster than JVM can run. And that's because Mill has a Graal launcher and Graal client and a long-lived JVM backend. So around JPS, you'll see this Mill server main in the background. So this is similar to Gradle or Bazel, where we start the long-lived server that is allowed to get hot and high performance. And we have a small Graal launcher that kind of talks to it, sends the command over, and receives the response. And we need to do that because the Graal native is quite limited, so you can't do things like class loading or reflection or other things in Graal, and many libraries don't work in Graal. So we just have Graal as a kind of front end for Mill, but the back end is just a long-lived JVM. Yeah, and we do use make full use of all the JVM features. Like we do bytecode inspection, we do class loaders, we do Java reflect, we do runtime compilation, because like it's a build tool, right? Build tool's runtime is your compile time, so we need to compile stuff at runtime. So we need the JVM in the back, and we just have Graal in front. Yeah.
And also, it has tools to assemble into Graal your projects, I understand. No?
Yes, if you want to use Mill to make a Graal project, you can use the same Graal, like Graal helpers that Mill itself uses for itself.
Right. Yeah, I touched a little bit of Mill. In our company, we have a library that, in the moment we started, Mill, I think, was not already super. It didn't have a lot of plugins. Mainly, that was the main reason that we use SBT. But will have been great because we test against all the Spark versions since 3.0, but against all of them, not only the middle version, also the minor version, because we touch a few things underneath and. Will have been great because with SBT was a really pain.
Yeah, Mill's also a lot better than it was like 5 years ago. So things like parallelism didn't work as well back then, and things like caching validation weren't as robust. Now they're a lot more robust. So like if you want to use it now, it'll be a lot better than when you tried it before, probably. Yeah, and a lot of the features I showed didn't exist 4 to 5 years ago. Yeah, cool. Yeah.
Thank you.
I guess you are done. One more question? Sure.
So I saw that you support Java and Kotlin as well.
Yes.
Any plans to support Clojure?
No concrete plans. Yeah, I don't know enough about that ecosystem to really do it myself. If someone wants to do it, it could probably work. Yeah, because the Java Scala Kotlin support is a lot of shared code. All the JVM, class path, assembly, whatever is all exactly the same. So I assume Clojure will be similar, but I don't know enough about Clojure. Yeah, there's someone working on Android support. So Android is also half JVM adjacent. Yeah, and I guess if you look at the website, this is worth mentioning. Mill-build. There's also experimental Python, Java, and TypeScript support. So you can build like a Python project using Python deps. So if you have a big monorepo, you can have like Python code in one part and Java code or Scala code and JavaScript code and all compiled together and parallelized and all that together. So it's pretty experimental, but I'm hoping that this becomes usable and popular. Yeah, cool.
Okay, one question. I understand that there are many advantages in the backend, in the mill backend, in terms of parallelism and so forth. Okay, but did you consider reusing the SBT backend or core system libraries? Reusing this SBT backend and just implementing a direct style DSL front end to SBT?
I didn't, because I think it's pretty fundamental how the things are different. So SBT has a 4-dimensional scoping with task scoping, task configuration, project, and one more, I don't remember. And there's like object-oriented, like tree scoping. So like the fundamental data structures are just different in mill and SBT. So I don't think it will translate. You are able to translate it losslessly. Like you can translate it, but that won't really match. And like there's no way to convert a 4-dimensional matrix into a tree, like a mill tree, easily. Yeah. So I guess also SBT has a lot of very old code that isn't necessarily very good. So for example, SBT has its own IO module, and the mill like OSLib IO module is just a better version of it, better documented, better ergonomics and everything. Yeah. So there's a lot of this in SBT where it was a good project like 15 years ago, but it hasn't really been kind of kept up to date and improved as you'd expect after all the things you've learned in Scala community last 15 years. Like we don't write Scala the same way we do 15 years ago, but SBT hasn't really caught up in all the ways.
Okay. Thank you. Okay, so thank you very much.
Okay, cool. Thank you. I guess I can stop the screen share now. Should I stop the screen share?
Yeah, it's okay.
Okay. I hope people like it online as well.